Okay. Hello. All right, 5 more Leetcode problems, 106 to 110. Let's get started. Construct binary, start the timer. Start. Given, construct binary tree from in-order and post-order traversal. Oh boy, we had trouble with a similar one last stream. Given 2 integer arrays in order and post-order, where in order is the in-order traversal of a binary tree and post-order is the post-order traversal of the same tree, construct and return the binary tree. All right, so our strategy for this last time was basically at the end we want to have return tree node val equals val left equals build tree, self.build tree, left in order, left post order, and right is the right stuff. So our strategy is split in order and post order into left and right sublists. So first of all, all right, we have in order and post order. So we have trouble even figuring out what the root is. No, the root is going to be the last thing in the post order. The root will always be the last thing in the post order. So val equals post order -1. Then how do I know the left in order and how do I know the left post order? So in order and post order. So in order tells us where the split is going to happen. So everything to the left of 3 is there, everything to the right of 3 is here. So this is similar to last time also. Index equals in order dot index of val, and then immediately we know left in order equals in order up to index, and right in order is starting at index +1. So we've got the left subtree already. Or sorry, we've got the in order. We've got both in orders of the left and the right subtrees. So last time there was this trick where the index is the same index in the post order traversal. And it looks like that might still be the case. Basically, so we cut off the end of the post order to get rid of the -1, so like that. And then we split post order at I. Left post order equals post order, or at index, I mean. Right post order. Is there any chance that this does anything? Oh, obviously, if not in order, return none. How do we end up with something not in the list? Why don't we print out in order and post order? Okay, so that just means this index trick doesn't work the same way. So we start with this. It works on the first node. And then on the right side, we've got 1527 as the in order. And the post order doesn't include 15 because we cut it off. Okay, so we can't do the same trick. We have to figure out how do we know what's the post order list. What's the left and right post order? So in our first step, this is the right in order. The right in order for us here would be this. I guess actually, if I don't do the +1, then it's right. It actually gives the right answer. I mean, let's submit it and see. Okay, there it is. So exactly the same trick as last time works. Last time I had trouble understanding why the index should be the same in both lists. And we looked at some solutions, and I can't remember if I was ever satisfied that now it made sense. No, everyone was doing this build thing. I never understood this strategy. yeah, this recursive thing. Where you're mutating some global thing and you've got indexes on the left and right side. Maybe this is my solution here. This is the same as what I'm doing. Yeah, remove from the right side. This is exactly the same as what I'm doing. Oh, how are they passing the same? Oh, interesting. You don't have to figure out left and right post order. You can just pass the whole post order down as long as you keep popping off the thing on the right. That makes sense, actually. So I don't have to do this. I can just pass the same post order to both. Don't do this. Okay, that doesn't work for me. What am I doing differently than? What am I doing differently than this person? They return root. Find the index of val. Oh. Oh, okay. Yeah, they're just doing right first, but this is the same as mine. Why is that different? Why can't I just say post order here and it be the same solution? Very confusing. Is it because of the order of... No, the order should be the same. Is it because they're mutating the post order and they have to go right first? That's probably it, actually. It's because they have to pop it off on the right side first. Okay. Okay, so if that doesn't make sense, I was saying the difference here is that they do this line before this line. So post order gets passed down and then mutated inside this, so that by the time you come here, it's got all the things from the right side already popped off. Whereas what I'm doing, the left and the right are independent because I'm splitting the list correctly from the beginning, so it doesn't matter what gets popped off either side. I'm never mutating my input either, so everything stays pure, like in the functional sense. So I think this one might be faster, but this one is probably easier to understand. in my opinion, because there's no mutating of objects that are being called or that are being passed in. All right, let's go to the next one. Start our timer. More binary trees. Given the root of a binary tree, return the bottom-up level order traversal of its nodes values from left to right, level from leaf to root. Okay. This is the same basically as one of the questions from last stream. You could just take the solution and then right at the end reverse the list. But let's just do it from scratch as though we hadn't seen that other solution. So the deal here is you just do a traversal. You remember what you want to return. What you want to return is a list of ints. You do a tree traversal. And you insert each value into, and what did they expect to return? Just the values? Okay. Insert each value into the correct place in ret as we go. So def traverse node tree node. We'll do some stuff and then return ret at the end here. So I'm trying to think of a way to do this that isn't just doing the exact same thing as last time and then reversing the list at the end. The problem is you don't know how deep the tree is going to be, so you don't know where to put things until you've gotten to the bottommost path. So I could start by traversing the tree to try to find how deep it is, and then now that I know how deep it is, I can traverse the tree again and put things in the right spot from the beginning. But that's going to be just as slow as traversing it and then flipping it at the end. So I think I am going to just end up doing that, even though that's not what I wanted to do. Reversed. Bottom up level order, left to right, so I don't have to change the values inside the list. Okay, so then we're just going to write the same thing as last time. Let's see if we can do it just from thinking about how it should be done instead of reading it. So you traverse from the root, and then you return ret. What does traverse mean? It means you are traversing node.left and node.right. If node.left, you do that. If node.right, you do that. And then you put the val in the right place. So node.val. How do you know what the right place is? You have to keep track of depth. So depth starts at 0. Here, depth is the depth that we were plus 1 because we're going 1 deeper. Ret at depth. You add this value to that list. Then how do I know that there's always going to be something there? We'll have to say if depth is greater or equal to len of ret, then we need to add a new list to ret so that we grow the list as we go. Okay, we just need to cast this to a list at the end. None type object has no attribute val. How is node? Oh, because they're passing it. Okay. All right, then we can just change this to say if node, change this to be node or none. If not node, you just return. And then we don't need these anymore because we're handling the none state inside the call. Oh, okay. Well, we can just start with an empty list and add the new list as we go, because that's what it wants for that base state. Submit. Boom, 0 milliseconds, 100. On to the next. We did that in 6 minutes. Restart the timer. Convert sorted array to binary search tree. Given an integer array nums where the elements are sorted in ascending order, convert it to a height balanced binary search tree. Okay. So a height balanced binary search, oh, they are explaining it right here, is a tree in which the depth of the two subtrees of every node never differs by more than one. So it's a binary search tree where you're kind of using up all of the space that you can, or not all, but enough that it has some nice properties around how the depth of the tree is log of the number of nodes in the tree. It's useful for binary searching because if you are going down the tree and you turn left or right at each fork, you know that you never have to go down more than log of n steps. So the balancing algorithm for binary search tree data structures is kind of complicated. Because they're labeling this as easy, I'm assuming I don't have to implement all of the complication of the balancing algorithm, and there's some easy way to go from sorted list to balanced tree. So without like building all the intermediate trees in between. So let's see if we can think of a way to do that. We basically have the in-order traversal. That's what having a sorted list is. So I guess that means you can just skip to the middle, put that as a root. You know the left subtree is going to have that stuff. You know the right subtree is going to have that stuff. And then for each of those, you do the same thing. So let's just do that. Sorted array to BST. Basically, val is equal to nums of len of nums over 2. So this is the midpoint. the mid index. Then basically return tree node where val is equal to nums at the mid index. Left is equal to sorted array to BST of nums up to the mid index, and right is starting from the mid index excluding mid. Then we have to handle the case where if our list is empty, then return none, because that's a valid value to put inside a tree, a node of a tree. And then here we need to say self. How can mid index be out of range? Well, I guess we want a number between 0 and len of nums minus 1. How can this be? What number are we seeing? Print mid index and nums. Oh, yeah, if this is the mid index, then I don't want to do that. I just want to do this. I was taking the value, but I meant for it to be the index. So let's try submitting this. There it is. Easy peasy. So just to explain one more time, a balanced binary tree is one where you're using up as much of the available nodes as you can, so you don't have a bunch of nodes where one or both of the children of it is none. And I mean, you don't have a bunch of intermediate nodes that are not using up both of their children. You're trying to make the height of the tree as low as possible. That's basically what the point of making a balanced binary tree is. Each time that you go left or right from the top, you want that to cut out half of the tree. That's another way to say it. That's also why it becomes log n height. So if our goal is to just use up all the slots in the tree, and we have an inordered list, we can jump to the middle and say that's our root. Left subtree is made of this stuff, right subtree is made of this stuff. And recursively do that. And every time we do, we're putting as much as we can. We're balancing the tree. We're putting as much in the left as we're putting on the right, so we end up with a height balanced tree. On to 109. And let's start the timer. 109, convert sorted list to binary search tree. Given the head of a singly linked list where elements are sorted in ascending order, convert it to a height balanced binary tree. Okay. Okay, so immediately I can think of two ways to do this. One of them is to do is to basically start by converting the linked list to a non-linked list and then use our solution from the last problem. The reason we have to use a non-linked list is because we have to jump to the middle index at each step. The other thing that I can think of is to have, well, we could use the full algorithm for constructing binary search trees iteratively, where we start by making -10 the root, and then we get -3, and we figure out how we can rebalance the tree when we insert that, and then we have 0, we figure out how we can rebalance the tree when we insert that. That's going to be really complicated, and it's not going to be faster than the stupid way of doing it, because the stupid way of doing it is on time to go through the list once, and then on time to build the tree after you've done that, so it ends up being on overall. It uses on space because you can't avoid using on space because the returned object uses on space. Often people will talk about the working space, so that's the amount of space it uses excluding the space you need to return the answer. And the stupid thing I'm saying would use on working space because you have to store the list. You have to convert the list into a different format and store it as an intermediate step. Whereas you wouldn't have to store anything extra if you do the intermediate trees. But the intermediate trees would be slow. I think it's either O1 or O log of n to insert a new node into an already balanced binary tree. I think it's O1. I think there's ways of doing it that preserve the balance property while only modifying a constant number of nodes. But I'm not actually sure about that. We can look that up after we're done. So my stupid solution would use more space than optimal. Let's see if we can think of a slightly better answer. So the thing that we have over the general rebalancing algorithm is that we know we're going to receive our next nodes in order. So is there a way that we can start by putting this in the bottom left and then put this as the parent of it, and then this as the right child, and then remember we were up here and go back up and add this as the parent of that? It sounds possible. Basically building the tree from the in-order traversal. And you're always putting stuff in the next slot where it goes. You would have to know how many elements you're going to have in order to proactively decide where things go, I think. Would you? I mean, in this example, they put, yeah, I guess you always have a choice of whether you want to put the next thing as the parent of the last thing, like the right parent of the last thing, or the right child of the last thing. Those are both allowed in a binary search tree. Not just the last thing, the right parent of something. Well, I guess it would always have to be, you'd have a, yeah, it'd have to be the right parent of the last thing or the right child of something that you've, no, it can't be of something. You can't, like, we couldn't go over here and put the 9 on the right here, because then it wouldn't be on the left of there. So there's always only 2 places where you could put something. Right? You can always only ever put it on the right of the node that you've just placed, or as the parent of the node, not the node you've just placed, but the node that your current root. At each step, either add to the right of the last node, or add as the right parent, add, yeah, to the, as the right parent of the root. And how would you decide which one of those to do? Actually, the way you decide, oh no, I was going to say the way you decide is you always prefer to add as the right child. But then in this example, you'd have -10, then 3, then you would put 0 over here, then you'd put 9 up here, or, oh, never mind, this isn't right either. This isn't right either. The other thing you could do is put something as the left. I forgot all about left subtrees. Like this 5 is on the left of this 9. This isn't right. All right, then let's think a little more about how to do this with no extra working space, and then if we can't think of a way very quickly to do that, we'll just do our stupid thing, which is still optimal in time, on, but uses on working space. And then we'll take a look at the solutions. So the first node becomes your bottom left. That's not negotiable. Then your next node must become its parent. on the right. Then is there a way to say, no. You kind of have to know how many there are going to be. Because sometimes you have to think ahead and not put the next one here, but skip one, put the 9, and then put the last one here. So I'm not seeing a way to do this. Well, no, there is a way to do it with the full rebalancing algorithm, which I don't know off the top of my head and would take me a very long time to derive from scratch. So I think I'm going to go with the solution I've thought of already, which is just to do the same as the last problem. So let's try to do it without looking at our answer for the last problem. L is equal to an empty list for cur in while cur, and cur is equal to head. We can just while head L dot append head dot val. Head equals head dot next. So now we've got our list, and now we just do the same thing as last time, which is mid equals L len of L minus 1 over 2, return self dot, or actually return tree node, where val is L of mid, left is L up to mid, and right is L starting at mid plus 1. I did forget a comma, but I'm also forgetting to handle when head when there's no list. So if not L, return none. Unhashable type list. When am I trying to hash a list? Am I returning a list somewhere? Oh, yes, I am, because this, I forgot to do self.sorted list to BST of this thing. Or wait, actually, you can't do that because you're supposed to pass in a linked list. So all right, here's like an intermediate answer without, because here I could just implement the last version of this that doesn't take a linked list, but let's try to play it by its rules a little bit. So instead of building L, let's not have L. Let's just figure out the length of cur equals head. Figure out the length of the list. Length equals 0. length plus equals 1. Once we have the length of the list, we know what the midpoint is supposed to be. I'm thinking there's a 2-pointer way to do this also, but actually it's kind of nice because then you don't have to iterate over the list again. So what I was going to do is iterate over the list again to find the head of the midpoint. But instead, let's do the 2-pointer answer where mid starts at 0. We're not trying to figure out the length. It's just that current is head. Or current, let's not have a current, we'll just have a mid, which starts at head, and an end, which starts at head. We don't care about the length. We already defined mid. While end, let's do while end. Mid goes forward by 1, end goes forward by 2 each time. So at the end of this, end is at the end, and we don't care about it. And mid is in the middle, and we do care about it. So val is mid.val. Left is mid, or head. Right is mid. Kind of. Now I have to split the list in half. Or I have to, yeah. So mid.next needs to finish. So right could be starting at mid.next. Then you've got head and right. I'll explain this in a second because I know this was probably hard to follow. List node object has no attribute left. List node object. I'm returning a list node somewhere when I shouldn't be. Oh, I'm doing the same thing again. This needs to be self.sorted list to BST of that list. Maximum recursion depth exceeded makes me think that I'm not splitting the list in half each time the way I want to. Though I'm not sure why, so I think it's time to put some print statements. Print head.val, mid.val, end. So we start with -10. Then we're saying 5 is our midpoint, is that right? What is the test case? It's off by 1. I was thinking the off by 1s don't matter, but they might. I'm not sure if they matter, but let's see what the first problem is. Then in the next, we're saying -10 is the left and 0 is the mid. And then we're saying that again over and over and over again. So the problem is we never shrink all the way down to a list of no elements. Which makes sense. There's no way to do that with this. And should probably start at head.next. Mid should start. Actually, I think this is, well, if I do this, does it solve the off by 1 issue? And then from there, I can just check if I have no head.next. -10, -3. So here we're saying the head is -10, the midpoint's -3. And the end is off the map. Which probably means, why don't I just print all of head right here? This probably means we're getting -10, -3. Oh, just -10, -3, and then I'm saying the mid is -3. If that happens, I think I want the mid to be -10, because mid.next is where right starts. So if you have 2 elements in your list, I want to split it halfway. No, actually, one of them needs to be the val. So I don't want to split it halfway. I do want to split it so that one's empty, the other one isn't. All right, well, one thing that's obviously missing is if not head, return none. So I don't think we've actually run into that issue yet. Okay, now our issue is our list is -10, -3. And I'm taking -3 as my mid, as my val. I'm passing nothing to the right side. Let's print right. I'm passing nothing to the right side, which is good. But then on the left side, I'm still passing... mid is still part of the left list. And that makes sense because I'm saying mid.next is... is none. What I want is like the one before mid should point to none. So let's try that. Prev equals, what are these called? List nodes. So we start with a dummy node whose next is equal to head. And then at each step, prev equals mid. Now here we can just say prev.next is none. Okay, why is that not working? Oh, because I need to do this before reassigning mid. Okay, that part's working now, but now I'm not handling the case where my list is one element long. So if my list is one element long, I would want mid to be the first element. Why isn't that happening actually? So if head is just one element, so no head.next, mid starts as head, which is what I want. End starts as none, so this doesn't happen. Right would be none. Prev.next, prev would be my dummy node, so this would be gone. I mean, this doesn't matter. It doesn't matter what happens here because this is still a dummy node. When I print here, I would see negative 10, negative 10, none. And then when I return, this is right, but head still exists. I didn't get rid of head. I didn't get rid of head. The way to fix that would be to have my own dummy head. Head equals list node, next equals head. Like, call it dummy. Don't actually pass head, pass dummy.next. So that prev should start at dummy. I think this will work. I think I just forgot to make sure they were the same thing. Okay, now let's submit this. This took much longer than than it should have, because we tried to solve this problem as a linked list problem instead of just converting it to a list first. This has the same issues. This still takes on. No, you know what? This takes no extra space. But we do have to traverse up to n each time. We have to traverse up to n in the first one. In the next one, we have to traverse up to half of n. In the next one, we have to traverse up to half of n. So I think this is like, and then on the bottom, there are log many things that we have to traverse in O1. I believe that makes us n log n time instead of n time. All right, so we have two solutions that are trade-offs of each other. We could do this in on space and on time by converting this into the last problem and solving the last problem. Or we could do this in n log n time and O1 space, which is what we did. I'm guessing there's we also know there's a way to get the best of both worlds, I think, if I'm right about the runtime of balancing a binary tree. But yeah, let's see how other people did this. Divide and conquer, space O1, n log n time. That's what we did. Divide and conquer on time, log n space. That's better. That's another trade-off. Is there one that gets O1 space and on time? No. Oh, this one claims to. But it's wrong because it's creating the list and then solving the last problem. So that list takes O n space. So this is not true. Okay, so this is actually a more interesting problem than I thought, because I thought we were missing something simple, but it looks like our solution is on the efficient frontier. This is O1 space. This is what we're doing. This is the same as what we're doing. Log n auxiliary space. That's interesting. And on time, I assume. They didn't specify. This is exactly what we're doing. Why did they say it's log n auxiliary space? Oh, I guess I was saying it's O1 auxiliary space because at each node you're only using O1 more space. But because of the recursive tree that has to be because of the backtracking, basically, that's inherent in the recursive algorithm, at the moment when it has the most memory, it'll have all of the leaf nodes in memory at once. I think that's what it is. They didn't provide an explanation. But yeah, so I think we did the same thing as them, and they probably have a more accurate analysis of the time than we did. Okay, let's go next. 110. Reset stopwatch. 110, balanced binary tree. Given a binary tree, determine if it is height balanced. So height balanced means the depth of the two subtrees of every node never differs by more than one. So for each node, the depth of each subtree, the max depth of each subtree, never differs by more than one. So you are balanced if your left is balanced, root.left is balanced, and your right is balanced, and depth of root.left minus depth of root.right, absolute value of this is less than or equal to 1. This is right. This will involve two different recursions. But that's okay. Let's just do it. Depth, root, optional, tree node. But I use optional, I use or none. It's the recommendation in the linter that I'm used to anyway. This returns an int. This is just equal to max of depth of root.left, depth of root.right, 1 plus that. If not root, then it's 0. So this will work. Yeah, we need the same thing here. If not root, return true. If you have no children, you have the same number of left and right children. Submit, and then we can make this a little bit better by combining the two. Well, a few things we can do. So the first obvious kind of cheat is from functools import cache. Just slap a cache on there, or submit. That already puts us at 2 milliseconds. The thing I was thinking is, can we combine both recursions so that is balanced? Basically, we're only doing one recursion, and it returns the depth if it's balanced. Otherwise, it returns, -1 or something, and that or throws an exception or something, so that we're only ever checking one thing. So that would be like You do return this, but only if you are balanced. So left equals this. Right equals that. If abs of left minus right is less than or equal to 1, then you return what we expect. Else you return, I don't know, return infinity, negative infinity or something. Then here we would say I basically want to do something like return depth of root and cast that to a Boolean. The problem is I've said 0. Yeah, this is the silly way of doing it. Return true if depth of root is not negative infinity, else false. The other way to say that is return depth of root is not negative infinity. Why is this wrong? We don't need the cache anymore, but why is this not giving the right answer? Wish I could visualize this. It's not, maybe we should print, what does it say the depth is? Oh, you can't do is not like that. You have to do not equal. Oh, interesting. Okay. Yeah, so this should be faster and use less memory. It didn't end up being faster. Here's a few questions I have. I wonder if this is getting too crazy, but from math import inf, is inf what's inf minus inf? Not a number. What's abs of inf minus inf? Not a number. And is that less than or equal to 1? No. And what's max of inf and inf? Inf. So we could simplify this a little by just saying no, actually we can't. Why isn't this faster? Is the cache actually doing something? From functools import cache. I think it might be. Is it? It's. Am I retracing over the same nodes? No, I don't think I am. We always go left and right. Yeah, we're never retracing. Caching does not help. Why am I slow? Is it because of the weird inf stuff I'm doing? Maybe it's slower to deal with infinities? How could I be faster than this? Well, one weird way is, let's define a exception called not balanced. Raise not balanced. Try. This is weird. And it's fast as hell. And this part's kind of easy to read, actually. So let's call this returns depth if the tree is balanced. Else raises. I mean, that's obvious. Yeah, this is kind of easy to read. This is kind of weird. Basically, return true if you didn't throw an exception. Move that there. Make a little more sense. Except is not balanced. Not too shabby. Ended up with kind of a clever thing. Oh, maybe all of the variance has been random because I didn't change anything in that time. It was 5 milliseconds instead of 0. And that time it was 0. Interesting. Okay, maybe none of what we did mattered, but this is kind of a cool looking answer in the end. We actually solved it in 3 minutes and then spent a bunch of time doing nothing for no reason. And we also don't have any infinities anymore in this solution. All right, that's